A strange stillness settled over the California coast in the hours before the alert, almost as if the air itself sensed the shift beneath the surface. Fishermen along harbors from Crescent City to Oxnard noticed their depth gauges reading oddly shallow. Dock workers watched mooring lines pull taut at unusual angles. A few early rising hikers in the coastal ranges felt the ground behave with an unfamiliar stiffness beneath their feet, as if contours had changed overnight. Most chalked it up to faulty instruments, morning fog, or the lingering drowsiness of dawn. But deep within the servers of the United States Geological Survey, a very different picture was coming together, one that would prove impossible to ignore, impossible to dismiss, and impossible to forget. Tectonic sensors spread along the margins of the Pacific Plate began feeding in data before sunrise, showing a rapid but coherent vertical displacement along multiple points of the continental margin. At first, the numbers looked like noise, perhaps an error in calibration. But then the seafloor pressure sensors stationed miles offshore, designed to detect the slightest deviation in water column weight, registered synchronized anomalies. The readings weren't ambiguous, they weren't scattered, random, or contradictory. They were unmistakable, something had pushed upward. The coastline, segments of it stretching for hundreds of miles, had risen. By the time analysts verified the data, the shift had already cascaded through multiple monitoring systems. Ground-based GPS stations, the same ones that detect crustal flexing in millimeters, all reported elevations slightly but decisively higher than mere hours before. The numbers told a story of abrupt uplift, a kind that rearranged the land in ways invisible to casual observers but undeniable to scientific eyes. And it was in those tense minutes, as the implications unfurled, that the USGS issued the alert no coastal resident ever expected to see in their lifetime. Red alert, significant tectonic uplift event detected along the California coastline. The message rippled outward with an immediacy reserved for truly extraordinary events. Researchers who had dedicated entire careers to incremental shifts and long-term structural deformations suddenly found themselves staring at a phenomenon that bypassed the slow evolution of fault mechanics and jumped straight into the extraordinary. This uplift wasn't something that would be measured over decades. It occurred between one tide cycle and the next. The implications were as vast as they were unsettling. Any sudden vertical motion along a coastline suggests the crust has been forced upward by processes happening far below, where tectonic pressures build silently over years, centuries, even millennia. It implied a rearranging of stresses, a redistribution of forces, a change in the subterranean dynamics that shaped the entire state's geological identity. Such a shift meant that the margin of California, one of the most studied, monitored, and historically active tectonic interfaces in the world, had just done something unexpected. Word spread swiftly across scientific communities. Seismologists exchanged messages, each referencing data streams they hoped would contradict the USGS report but didn't. Geophysicists studied the uplift pattern for hints about which faults were involved. Marine geologists rushed to understand whether the seafloor had moved uniformly or in staggered blocks. The elevation changes detected were small in absolute terms, measured in centimeters rather than meters, but the scale and coordinative precision of the event were what elevated it from a geological curiosity to a red alert level anomaly. For people living along the coast, the physical effects weren't immediately dramatic. Beaches didn't suddenly stretch outward in visible new expanses, cliffs didn't jut noticeably higher, roads didn't buckle overnight. Yet to the trained eye, the differences were real. Some tidal pools sat slightly higher above the morning tide line. Channels that once comfortably accommodated boats felt tighter. A few piers leaned just a touch more noticeably than the day before. These subtle manifestations were easily overlooked by anyone not actively searching for them, but they hinted at something immense, something that changed the relationship between land and sea. What perplexed researchers more than anything was the silence that accompanied the uplift. Typically, any rapid vertical displacement of the crust is preceded or followed by seismic activity. There are foreshocks, indicators, tremors, or rumblings that betray the work happening beneath the Earth's surface, but the sensors had picked up almost nothing. The coastline lifted without the expected chorus of quakes, as if some mechanism deep underground had shifted its configuration smoothly, yet with incredible force. The Pacific Plate had nudged, tilted, or flexed in a way rarely observed and scarcely documented. As experts scrambled to decode the event, attention shifted toward the broader tectonic architecture of the region. California's coastline rides the boundary between two massive plates, the North American Plate and the Pacific Plate, locked in a gradual but relentless struggle of motion. Most public discussions focus on lateral movement, the infamous strike-slip behavior of the San Andreas Fault, yet the state's tectonics are far more complex. Dozens of faults crisscross the region, each capable of interacting with the others in subtle or profound ways. A sudden uplift hinted that deep pressure, long confined, might be redistributing along new pathways. Some suggested that the uplift might originate from subcrustal forces pushing upward, the kind that reshaped fault zones in ways invisible to surface dwellers until a moment of release. Others examined historical records for precedents and found few analogs. What added to the intrigue was the spatial alignment of the uplift readings. Rather than isolated patches rising independently, the uplift followed a broad, sweeping curve that hugged much of the coastline. It was as if the entire edge of California had been nudged upward by a unified push from below. Researchers debated the scale of what had happened. Vertical displacement of even a few centimeters, when spread across hundreds of miles, represented a monumental geological event. The crust isn't a flexible material that bends easily. It fractures, cracks, and grinds into new equilibrium. That the coastline could lift as a contiguous structure suggested an incredible amount of integrated pressure release or redistribution. Some speculated that deep-seated faults, ones that rarely make headlines, might have realigned. Others considered that a broader segment of the Pacific Plate had shifted vertically rather than horizontally, causing an unusual style of deformation. The USGS Red Alert wasn't issued lightly. Such alerts are reserved for events with the potential for cascading consequences. In this scenario, the concern centered on what the uplift revealed about the current state of tectonic stress. A shift upward meant something important had occurred along the plate boundary, something significant enough to change elevation itself, and any change of that magnitude demanded scrutiny. Attention quickly turned to the implications. Uplift changes coastal dynamics. It alters the baseline for tides, storm surges, and erosion. It can modify groundwater flow, affecting aquifers near the coast. It can change the stability of cliffs and slopes, especially those already prone to landslides. Even subtle changes can influence the long-term behavior of faults that intersect the coastal zone. Engineers and city planners would eventually have to consider how this shift, small though it seemed, might modify the assumptions on which infrastructure near the coast had been built. In the scientific community, one of the most immediate implications was the need to reassess existing models. Prior to the uplift, researchers believed they had a relatively stable understanding of how stress accumulated and released along the California coast. Yet the sudden uplift challenged many of these assumptions. If the crust could rise without a major quake or volcanic event, then the forces at play might be more complex than previously thought. The models used to predict long-term fault behavior would need revisiting. For many scientists, the uplift also raised questions about interactions between offshore faults and the more well-known systems on land. The seafloor off California is a labyrinth of fractures, ridges, and fault strands that often slip under the radar due to the difficulty of studying them in detail. If one of these offshore faults had shifted, it might be affecting stress distributions inland in ways not yet understood. The connected nature of tectonic systems meant that a disturbance offshore could ripple through interconnected structures both near and far. Coastal ecosystems also face profound implications. A slight change in elevation can shift the delicate balance that sustains tidal habitats. Certain species rely on exact ranges of water coverage. Altering that balance could change the distribution of organisms that define coastal ecology. While the uplift described here was modest in immediate visible effect, its long-term consequences could be significant for the plants and animals that depend on stable conditions along the intertidal zone.